In this video, we use the integrated rate laws to derive relationships that allow us to determine the half-life of chemical reactions. We've seen this table a couple of times now, a table summarising some of the most important relationships associated with reactions of different order. In this video, we focus on the bottom line of the table, which refers to the half-life of chemical reactions. The half-life, T-half, of a chemical reaction is the time required for the concentration of a reactant to drop to 1/2 of its original value. The half-life refers to a time interval, and so the SI unit for half-life is the second. However, with many chemical reactions taking place over minutes, hours, years, or even millions of years, it is not uncommon to see the half-life quoted in these other time units. The half-life is a convenient way to express how fast a reaction proceeds. Fast reactions are characterized by a short half-life, or small values of T-half, and large values of the rate constant K. Slow reactions are characterized by a long half-life, or large values of T-half, and small values of the rate constant K. We can use the integrated rate laws to readily derive expressions for the half-life of zero, first, and second order reactions by considering that the half-life is defined as the time taken for a reactant to drop to half its original concentration, and so we can set the concentration at time t to be equal to half the initial concentration and substitute this value into the integrated rate law expressions. For example, we'll start with the half-life for first-order processes, which are the most common and most important. The integrated rate law for a first-order reaction can be written as this equation here, but we have seen that this equation can be rearranged to a sometimes more convenient form shown here. Given that, at the half-life of a reaction, the concentration of the reactant A equals half of the original concentration, we can make the appropriate substitution to get this expression here. The left-hand side of this expression simplifies to the natural log of 2, and solving for T-half, we get T-half equals ln2 divided by K, or T-half equals 0.693 divided by K to 3 significant figures. Since the rate constant K is a constant at a given temperature, we see that the half-life for a particular first-order reaction is also a constant at a given temperature. In other words, at a given temperature, the half-life of a first-order reaction is independent of the initial reactant concentration and only dependent on the value of K. This means that for a first-order reaction, the half-life remains constant throughout the course of the chemical reaction. For example, imagine a first-order reaction where reactant A is converted to product B. If we start with initial concentration of A of, say, 1.6 molar, and the concentration drops to 0.80 molar after, say, 10 seconds, we say that the half-life of the reaction is 10 seconds. For a first-order reaction, if we wait another 10 seconds, which is a period of time equivalent to the half-life, the concentration will drop to 0.40 molar. And if we wait another 10 seconds, or another half-life, the concentration will drop to 0.20 molar, and so on. In other words, it doesn't matter what concentration we start with, the half-life will be the same, 10 seconds in this case. This is not the case for a second-order reaction, where we see that if we make the same substitution, we get an expression for the half-life that is dependent on the initial concentration of A. Doing the same for the zero-order case and making the appropriate substitution, we get the half-life being equal to the initial concentration divided by 2K. In both cases, we see that the half-life is dependent on the initial reactant concentration, and the half-life will therefore change during the course of a reaction as the concentration of reactant changes. In the case of a second-order reaction, the lower the initial concentration, the longer the half-life. In the case of a zero-order reaction, the greater the initial reactant concentration, the longer the half-life.